quickly. I mean, this is a complete game changer in the field, and it was adopted very rapidly over the course of, let's say, 5 years. Quite a community. Okay, any other questions? Oh, yeah. You mean when the North Pole is in the north or in the south? I was simplifying significantly. I mean, all that really matters is that the orientation of the Earth's field changes when it goes backwards and forwards. And so whenever you're at a particular point on the Earth's surface, the largest portion of the signal you're measuring is today's magnetic field. But it's modified very slightly by what we call remnant magnetization, which is the frozen-in magnetization in the crust. Okay? And so that frozen-in magnetization, if the orientation of the Earth's magnetic field is the same as today's, then that frozen-in magnetization amplifies the magnetic field a little bit. And if it was the opposite way around, then it decreases it a little bit. Okay? Any other questions? Okay. Okay, so the question now becomes, this is an earthquakes class, who is at risk from earthquakes? Right, people, first order observation, earthquake risk is focused on the edges of the plates, because that's where most of the earthquakes occur, right, is at the margins of the plates. So it's only if you have a population center that is essentially on the edge of the plate, like the Bay Area, for example, that you have any earthquake risk, okay? But these other regions, away from plate boundaries, and there are exceptions, as was just pointed out in China, then they are basically in safer locations, okay? All right, so we can take this magnetization thing a step further, okay? Now that we can actually use the magnetization that we can measure on all of the oceans. You can only do this in the ocean, okay? And you can use it to essentially, as a magnetic tape recorder, and you can put dates associated with these flips in the Earth's magnetic field, and you can then essentially wind back this magnetic tape recorder. Sort of one reversal at a time, you can wind it back, remove that strip of oceanic crust. So you go to the first reversal, and you remove it from, this is the East Pacific rise, you remove it from the East Pacific rise, this is the Atlantic. You remove it from down the Mid-Atlantic ridge, and then you go to the next reversal, you remove that, and as you go back in time, you can reconstruct how the plates have moved. Right? So in the case of the Atlantic, as you go back in time, of course, the total width of the Atlantic is reduced, and as you go further and further back in time, South America comes into contact with Africa, and North America comes into contact with Eurasia. All right, so we can reconstruct these plate motions. This is what the globe looks like today. Just by removing these strips of the Earth's continents, we can reconstruct what the continents look like on the surface of the Earth as we go back in time. And we can do that back about 200 million years. We can only, and I say only, remember that the Earth is billions of years old, we can only go back 200 million years because that's the age of the oldest oceans. You can't see the color excuse me. You can't see the color scale here. The color scale is showing you the age of the oceans. Okay, so red is obviously the most recent, through yellow, green, and blue. This dark blue color, you can see it around the margins of the Atlantic, is the oldest oceans. So you can only go back about 200 million years, and then you've basically removed all of the ocean that exists, so you can't go any further back using this approach. There are other approaches, but you can only go 200 years back. So what can we say, just looking at the age along the Atlantic, what can we say about the relative times when the Atlantic started to open up? Anybody want to tell me the history of the North Atlantic, not the North Atlantic, the whole Atlantic, the Atlantic Ocean? When did the continents start to separate? Say again? 1600? Where did you get 1600 from? Okay, it was long. It was. That's very recent. Okay, I'm obviously asking the question too oblique. Yes. Okay, so yes, so the Atlantic started to separate about 200 million years ago because there's some blue up here. What I'm trying to get at here is that the North Atlantic started to separate earlier than the South Atlantic. That's what I was trying to get at, right? Because you can see these blue sections here, and they are about, I think, if I remember, this is, well, the North Atlantic started to separate about 180 million years ago. The South Atlantic started to separate more recently. There's no blue age. There's none of the really old oceanic crust, okay? So in fact, it was Eurasia and North America that started to separate, and then later, Africa and South America started to separate, okay? So that's how we reconstruct plate motions. Okay, so now I kind of want to run through the different categories of oceanic plates, of plate boundaries, so that you understand what they are. There are 3 of them. It's very straightforward. But also, the reason it's important to know what these are is it tells us something about the kinds of earthquakes and the kinds of hazards that we find at each of these boundaries. Okay, so the 3 categories of plate boundary. The first is a divergent plate boundary. So this is obviously where plates are moving away from one another. And so the Atlantic is, of course, an example of a divergent plate boundary. So in a divergent plate boundary, you have to be creating new crust to the Earth. All right, as these plates move apart, magma upwells in between, and you create new plate, and specifically new ocean. It's all of this deformation, all of this creation and destruction of plates happens in the oceans. The continents are forever, as they say. Okay, the second category is a transform type plate boundary, where the 2 plates are moving, sliding past one another. So there's no creation and there's no destruction of oceanic plates. And you see that in both the oceans and in the continents. And then the third one is a convergent plate boundary, where 2 plates are moving towards one another. And that means, of course, that you have to destroy plate. Okay? And you can have convergent plate boundaries between an oceanic plate and a continental plate, between an oceanic plate and an oceanic plate, or between a continent and a continent. Okay, so any of these combinations. So a divergent is always ocean-ocean, right? Because it has to be ocean on either side. A transform can be in the oceans or in the continents, and a convergent can be a collision of any type, any combination of either ocean or continent. So we're going to talk about them in more detail. But what kinds of faults do you expect that we're going to find at divergent plate boundaries? You should know this. It could well be on the exam. Normal faults, exactly. So normal faults are the kinds of faults you get in extensional environments. So a divergent environment is an extensional environment. What type of faults do you get at transforms? Strike-slip faults, okay? And then at convergent boundaries? Reverse or thrust fault, same thing, okay? And so if you know what type of earthquake you have, or what type of faulting you have, whether it's a convergent, whether it's a thrust, a normal, or a strike-slip fault, you can say something about the type of plate boundary. So now these earthquakes are not only telling us where the plate boundaries are, they're telling us the type of deformation that's occurring on this plate boundary. So some examples of these, divergent plate boundaries in the Mid-Atlantic Ridge, the East African Rift. So the East African Rift, I said that divergents are only between ocean and ocean. So this, of course, is not ocean-ocean. There are actually 2 continents, the Arabian plate and the African plate here. But they are moving apart. And so the East African Rift right here down the Red Sea, that is the beginnings of a new ocean. Come back in a few million years and there'll be an ocean between the Arabian plate and the African plate. Okay? Transform faults, of course, the San Andreas fault is a great example. And then convergent boundaries. Well, we're going to talk about some of these examples. Okay, so let's start with the divergent boundary, the mid-Atlantic ridge. And so, again, the idea here is that as these plates are pulled apart, so that you can think of it as the continents that just continue to move. As the continents continue to separate, there's essentially a gap, there's a vacuum that forms between these two plates. And needless to say, that means that material upwells, the material that's under pressure in the Earth's interior upwells into this gap. As it moves towards the surface, the pressure on it is decreased, right? So as you move towards the Earth's surface, the pressure decreases. And as the pressure decreases, that allows this material to melt. So material that's down here at depth is solid, but it flows, it's a viscous solid. And so as you create a gap, material flows up, the pressure is reduced, it melts, and that's how you create new oceanic crust. And so this very thin black layer is the new oceanic crust. Oceanic crust is about 7 kilometers thick. And then this thicker material underneath is the restite. It's the material that's left after you've melted, and part of this upwelling material that forms the crust. So, of course, mid-ocean ridges are very interesting places because of all of this activity that's going on, this plate tectonic activity. And you get these black smokers. These black smokers are essentially fluids that are getting circulated through this new oceanic crust. They get superheated. They dissolve all kinds of minerals from the new crust, and then they get squirted out vents close to the ridge. So let's see if I can make this play. And so this is an example of a black smoker here, I guess, and another one here. So this is stuff that is coming out at 2.5 kilometers depth. This is being filmed using a submersible. And so this is very high temperature material. It turns black as it comes out because as the very hot fluid hits the surrounding seawater, it starts to cool, and the minerals that are in it start to precipitate out, and that's why you get these black smokers. So despite the fact that this is very high temperature and very deep in the ocean, because of the thermal energy and the mineralogy that is coming out of here, it's actually a very fertile place for biology. And so you find all kinds of very unusual marine life along the mid-ocean ridges that have all formed to live off this thermal energy and the mineralogy that is coming out of it. Okay? Second one is transform plate boundaries. So there are two types of transform plate boundaries. Okay? The first is oceanic transforms. Okay? The second, of course, is the San Andreas Fault. But the first is ocean transforms. And so this is a great example here in the South Pacific. So the mid-ocean ridge is this shallow bathymetry here. And you can see that the ridge obviously comes down here. It's then offset, continues down here. It's offset and continues down here. Right? Everybody can see that? So the ridge comes up here. The shallow bathymetry is the ridge. Up here it's offset, offset, and continues. And so you can see that there are lines in the bathymetry that are aligned with the offset in the ridge. But the lines are not just between this end of the ridge here and the beginning of it here. The lines continue for much greater distances along the ocean floor. And so these are what's called fracture zones. And it's obviously a major location of deformation on the oceanic plate. So if we sort of zoom in to one of these fracture zones or ocean transforms, this is what it looks like. So this is the mid-ocean ridge coming up here. It's offset by a transform. And then this is the mid-ocean ridge that continues here. So we have this offset, and you have this sort of fossil scarp here, which is as a result of having this offset. Okay? So if you stand there and what's the relative plate motion? How would you describe this fault motion? I think I heard some very different answers. Everybody's saying lateral. The question is it right lateral or is it left lateral? Okay. Okay, let's take a vote. Who thinks it's right lateral? And who thinks it's left lateral? Wow. You guys are in trouble on Thursday. So how do you tell? Somebody tell me how we identify if this is right lateral or left lateral. You sticking your hand up? Yeah. How do you tell? Okay. Yeah, right. To the left. Okay. So you stand on one side of the fault. So in this case, we're standing on this side of the fault. You look across to the other side of the fault, and you ask, is it going to the left or to the right? And so if you stand here and you look across here, it's moving to the left. Right? Now, of course, you can come to the other side of the fault, and you can stand here, and you can look across here, and it's still moving to the left. So this is a left lateral fault. Okay? You stand on one side, you look at the other side, and you ask whether it's moving to the left or the right. That's how you tell. All right? So if you stand here and you look to the other side of the fault, what's the motion? Say again? Right? Question? Why does it look like the offset is going to the right? Oh, okay, got it. So the question that's being asked here is if you look at the ridge, it looks like the ridge has moved to the right. That's true. Nothing to do with the relative motion of the fault. So the fault motion, so you're absolutely right that this is offset, this is to the right relative to this, but we're just talking about the motion of this fault. The way that this moves in this direction, so how do we get this separation? Well, the way that you get the separation, actually that actually doesn't help. I'll stop saying that. But all that matters here is that the fault, when you look at the fault, we're looking at the motion on this fault. We're not looking at the relative motion of these two ridges. We're looking at the motion of this on this fault. When you stand here and you look to the other side, it's moving to the left. They don't tell you, in the case of describing the motion on this fault, the relative location of these two ridges is irrelevant. That's right. Yeah. Say that again? No. Okay, now I think yeah. Remember, there's another component of motion here. These are separating, right? We're creating new ocean here. So if this was fixed, if this was suddenly frozen, and this motion continued, then this would gradually move closer to this. That's true. However, whether this moves closer to this or not is dependent upon how quickly this is creating new ocean. So the relative separation of these two ridges is determined by how quickly this is creating new ocean and how quickly this is creating new ocean. So it's a completely separate process. Yeah. Okay, so yeah, my question was, how do you describe the motion here? And say what you said again? That's right. It's a trick question. There is no motion here. These two are frozen together, right? So if this ridge is creating new plate at the same rate as this ridge, which is the norm, then that means that the velocity of this plate in this direction is the same as the velocity of this piece of plate in this direction. So once this plate has moved past the edge of the ridge, there's no relative motion here. Okay? Say that again? Sure. So there is only relative motion between this piece of plate and this piece of plate between the two ridges. Okay? So the norm for mid-ocean ridges is that the rate at which the oceanic plate is being created here is the same as the rate at which the oceanic plate is being created here. That means that this material is moving in this direction at the same rate, the same velocity that this material is moving in this direction. So between the two ridges, because this piece is moving in this direction and this piece here is moving in this direction, there is relative motion along here. However, as soon as this plate gets past the ridge on the other side, these two pieces are moving at exactly the same rate. So there's no relative motion. Okay? So I encourage you all to look at this diagram and just think this through so you understand this concept. But again, the motion on this fault here is a left lateral motion. There is no motion here, and there's no motion here. That's why we call these fracture zones rather than transform faults. We refer to the whole thing as a fracture zone because obviously there's a fracture. It used to be a fault, but it's only this central section that is an active fault today. These edge pieces, both this piece here and this piece, are no longer active. Okay? I can see this is a struggle. All right, let's keep going. So are these transform faults a hazard? I see some nodding heads. Does everybody agree that these transforms are a hazard? People are not sure? So the issue here is there anybody at risk from these faults? So the answer to that is no, okay? Just to again emphasize the difference between sort of where earthquakes are occurring and where there is a risk associated with it. So there obviously are going to be earthquakes along this transform fault. In fact, they're very productive in terms of earthquakes, but there's no people here, obviously, so in that sense, it doesn't present a risk, okay? All right, the other type of transform is the one that we're all much more familiar with, the San Andreas fault. And of course, this runs along a continent-ocean margin. There are pieces of the North American continent that have become part of the Pacific plate, right? Just because of the historic processes of this faulting, some pieces of the continent are actually now attached to the Pacific plate, which is mostly an oceanic plate. So that's why I say that Los Angeles is on the Pacific plate. As it turns out, Tokyo is on the North American plate. So Los Angeles is not part of the North American plate. San Francisco is part of the North American plate because the San Andreas fault is just offshore where it goes past San Francisco. In fact, I have this little delightful, very grainy video that shows the relative motion along the San Andreas fault. Okay, so Pacific plate on the left, North American plate on the right lateral strike-slip motion. So here we have San Francisco and Los Angeles, and over the course of about 10 or 11 million years, we will find that Los Angeles will just be a grimy little suburb of San Francisco. Even better, if you wait a few more tens of millions of years, Los Angeles will disappear down the Aleutian subduction zone. What can I say? I live in the Bay Area. Okay, so that's transform-type faults. So the last category is divergent plate boundaries. And this is sort of interesting because it really matters whether it's ocean-ocean, ocean-continent, or continent-continent as to what happens at these convergent plate boundaries. So here are the three types. So an ocean-ocean margin like this is one example is the Japan Trench. Here this is an ocean-continent margin, so this would be South America, would be an example. And then this is a continent-continent margin, and the Himalayas are an example of that. So you can see what happens when you have two continents. And the point here is that you can only subduct oceanic plate. So the reason that the continents are above sea level is because continental plate is more silicic, has more silica in it, it's less dense, it's lighter than oceanic plate. And so it literally floats higher relative to the oceanic plate. Okay, so that's why the oceanic plates are beneath the oceans and the continental plates are above the oceans. And because the continents are lighter and less dense, you cannot subduct them. You can't force them to go down into the Earth's interior, but you can make oceanic plates go down into the Earth's interior. Okay, so that's why there's this sort of interesting geometry that forms. We're going to look at these one at a time, I hope. What's going on? Okay, so these are just the examples. Okay, so let's start with South America. All right, another cartoon. So in South America, we have an oceanic plate that is subducting beneath the South American continental plate. Okay, so here's the oceanic plate. The oceanic plate is being pushed down. You can see some seamounts being pushed down. And as it gets pushed down into the mantle, it starts to heat up. Right, it's obviously basically it's at 0 degrees at the base of the oceans. As you push it down into the mantle, it starts to heat up. And as it starts to heat up, it starts to melt. And so that melt, of course, is very buoyant, very light compared to the surrounding rock. And so the melt gradually makes its way to the surface. And so, of course, that is why we have volcanoes at subduction zones. We talked about the fact that we see earthquakes and volcanoes in the same belts around the Pacific. Where you see earthquakes and volcanoes is where you have a subduction zone. The volcanoes, for the most part, not entirely, but for the most part, you find them above subduction zones. So you push oceanic material into the mantle, it starts to melt, the melt comes up to the surface, it erupts as volcanoes, and increases the overall thickness of the overriding plate. Okay? So this is an ocean subducting beneath a continent. You can also have an ocean subducting beneath an ocean. And in fact, the entire Japan, all of the islands that make Japan are all subduction zone volcanoes. So the entirety of Japan is basically built on top of volcanoes that have been created above a subduction zone. So it's not so surprising that Japan has such a serious earthquake problem. Okay, and then the last one is when you have a continent colliding with a continent. Okay, so you can imagine in this situation here, right, we have one continent and we have an ocean. Well, as this continues to subduct, eventually there's going to be another continent over here. Right? So eventually another continent is going to be pulled towards the South American continent by this subduction zone and they're going to collide. And that's exactly what happened where you have the Indian plate colliding with the Eurasian plate. There used to be an ocean there. All of that oceanic material has been subducted, and now you have these two continents that are colliding. The continents won't subduct, and so instead these two continents can continue to collide and form mountains, the Himalayas in this particular case. And so the Himalayas, of course, is a huge mountain range, but in fact, India only recently collided with Eurasia. And so India is still moving north at about, I think it's 9 centimeters per year, if I remember correctly. And so the Himalayas are going to continue to be pushed up until the plate actually stops moving. So this is the death of the ocean. The continental plate continues to collide. There's no longer material diving down, and you just start to form the Himalayan belt. Okay? Yeah, question? How big will it get? That's a great question. You mean how high will it get, right? So, of course, as it gets higher and higher, the gravitational energy that's needed to hold it up increases, right? So there's this trade-off, in fact, as you get higher and higher mountains, they erode faster and faster. So a lot of material is being eroded off the top, but eventually the two will stop moving towards one another just because the gravitational force needed is insufficient. Okay, finally, very quickly, I want to tell you a story about using plate tectonics as an earthquake predictor. Okay, so we just talked about the fact that there is only hazard where we have earthquakes, and we only have earthquakes at plate tectonic boundaries. So my question to you is, would we predict that we're going to have earthquakes along the San Andreas fault? Well, obviously the answer is yes. You would all say we're going to have